Hi everyone. Today, from this video recording, I'm going to cover section 3.1 again because last day I could not finish the entire section 3.1. However, through this video, I'm going to explain everything again that I discussed in the class last day. And also, there are a few slides I did not go through last day. So, I will, all in all, I will cover this section 3.1. Actually, this chapter 3.1, based on distributions and how we can deal with these distributions. So as a start of that, uh, I'll skip this outline. I told you, I explained you what is this statistical inference again. That we already know this one from chapter one, statistical inference, which is taking a sample from a population and then analyze this sample uh, to conclude about its population. So this is the process. This process we call statistical inference, and since we have these population and samples, I told you we use different notations. We discussed these notations earlier in our class. So we use different set of notations for the population. Those are measurements that we take in population, and also the same measurements but in the sample, but we use a different notations. So these notations that we use in the population, for example, in upcoming slide we have this mean, which is mu, standard deviation sigma, um, proportion simple p, correlation, which is rho. So these are the notations that we use for the measurements when we are dealing with the population. For the same measurements, if we are dealing with the sample, we have to use different notations. For the mean, x bar; for the standard deviation, simple s; for the sample proportion, p hat; and the correlation, simple r. Okay, so these are the measurements we use in the population and sample. Actually, there are four, but when we come to the population, notations are these, and the sample notations are these. So we have, you should know these distinguish between population notations and sample notations. So these notations or these measurements, when we are dealing with the population, we have a general name. We call those are parameters. Those are parameters. Okay, these notations or these measurements, if we are dealing with the sample, we call statistics. Okay, in the next slide you can see the definition of statistics and parameters clearly. However, this is the idea. Parameters, that means population measurements; statistics, that means sample measurements. Here statistics is not the subject. Our subject is statistics. This is statistics only for the sample measurements. So this is the definition of the parameter in statistics. It describes parameter. It describes some aspect of a population. So these are population measurements. So statistic, which is a sample measurements, because we compute them from a sample. So what we do here is simply we use these statistics to estimate these parameters. We use these statistics to estimate these parameters. That's what we do in this chapter, the entire chapter 3. This is what we do. We simply use statistics to estimate parameters. Okay, so with the population parameters and the statistics, this picture I have updated this one. So you can see this statistical inference, the same picture we used earlier. And this bridge, now you can understand, you should be able to understand what is going on with this red color cycle part, this part in the cycle. So from the sample to population, this is the conclusion. How we make the conclusion, that's actually based on this statistics and the parameters. So we simply estimates parameters right here using these statistics. That's how we made the conclusion. So clearly I have mentioned the parameters and statistics based on our measurements that we use in the past, in the actually in the class. Mean, proportion, standard deviation, correlation based on the population and the sample. So this is the population and this is the sample. Okay, so throughout this course you should be you should remember these notations, because in statistics notation plays a big deal. They play a big role. So whenever you use mu instead of x bar and you are dealing with a sample, then your problem, the answer is going to be wrong. So you have to know what you are dealing with. If it is population, you have to stick with the parameters. If it's a sample, you have to stick with the statistics. All right. uh, Sorry. So I also talked about these examples based on parameters or statistics. Actually, in these examples, you should first understand whether this scenario is population based or sample based. Then once you figure it out whether it's a sample or population, then you can decide we have to use statistics or parameters. Right, this first one, average household income. This is about average household income for all all houses in the US using data from US census. So I told you earlier in the class, whenever we are dealing with US census, this US census, they use the population. They use entire US population. So and also here they have mentioned all houses. That means we are dealing with the population. So we are dealing with the population. That means we need parameters. Which one? Average. That means parameter is mean. So population parameter mean. Okay. Right. The next one. Correlation between height and weight for players on 2014 Brazil World Cup team using data from all 23 players on the roster. So remember this, the population always based on the scope of the study. Okay, based on the scope of the study, we define the population. For example, if I need to know my class, students in my class heights and the weight, or the correlation between height and the weight of students in my class, that's all I need to know. So at that point, my interest is all about my class. So there are 24 students. So my population or the scope of my study is my classroom. So there are 24 students. The population in my case is 24 students. Okay. So remember, always stick with the goal or the scope of the study. So here their scope or their studying plan is for players on the 2014 World Cup team. Okay, so they are focusing on the correlation. That's the measurement. Correlation between height and the weight for players on 2014 Brazil World Cup team, and they use data from all 23 players in the roster. So they use all the players in the roster. So this is the scenario based on the population, because they have considered population. So we have to use correlation parameter. Correlation parameter. Okay, all right. So last one, it is super easy. I think that's the easiest one. A proportion of people who use an electric toothbrush using data from a sample of 300 adults. See, sample of 300 adults. So it is a sample. That means, so it's a sample. That means we have to use statistics. Statistic, which one? Proportion. So here measurement is proportion. So we use proportion statistic. Okay. All right. The all of these values, for example, this x bar, this simple s, p hat, let's say simple r, correlation. So these we use to estimate mu, sigma, simple p, and rho. Okay, so always map these estimates properly. Okay, do not swap them or do not map them here and there. Okay, so here mean always this sample mean always align with the population mean. Okay, so this x bar is the x bar we use x bar to estimate we use to estimate mu. Okay, so this x bar we call an estimator. Okay, so there, for example, in my case, let's say okay, let me write it down here. Let's say okay, x bar equals 5. In this case, x bar is the point, x bar is the point estimate. Actually point, that means always these, all of these values, they have one value. They give us just one value. X bar equals a value. Since we have a one value, we call it a point. So we call this, these are point estimators. So here x bar is the point estimator of mu. Okay, and also this 5, this value is the point estimate of mu. This is just an example. Okay, so in statistics, these point estimators and point estimates, they have a difference. You can see that x bar, this notation is the point estimator that holds the value. The value is the point estimate. Okay, here in this definition they have mentioned about the point estimate, definition based on the point estimates, the value. Okay, but in this course it doesn't matter, it's not a big deal for me. Although you mentioned it's a point estimator, point estimates, I know what you are talking about. So don't make things too harder in this course. So all in all, we can say x bar equals 5 is the point estimate for point estimate of population mean or population parameter mu. Or you don't have to mention population parameter, simply you can mention mu. That's okay. So the point estimator is that. So x bar is the point estimator of mu. Simple s is the point estimator of sigma. P hat is the point estimator of simple p. Or simple r is the point estimator of rho. Okay. So point estimate, see this one, point estimate will not match the population parameter or simply we call parameter exactly. Okay, it gives us it gives us a very approximate value. So in statistics I always mention that we don't need exact values, approximations are just fine. You have to remember these things. Statistics varies from sample to sample, because statistics purely depend on 100%, it depends on sample. This is the problem. This is the problem that we have in this section when we are dealing with this idea or this setting. The problem is when we take two samples and try to um, estimate the population parameter, whatever the parameter, doesn't matter, we will be having some problems. The problem is those values, those two statistics in those two samples, they are different. That's the problem. For example, let's say you have your population here, size is capital N, and I'm taking two samples. I'm taking two samples, sample number one, sample number two. Okay, same size doesn't matter, these two samples, and I'm calculating x bar. Simply say x bar for this sample and this sample. To make things clear, I'll use x1 bar and x2 bar. Okay, so in this case these are random random samples. You know what is the meaning of random sample. These are random samples. This x1 bar and x2 bar, they are different because we take these samples randomly. So I can use this x bar to estimate mu, and I can use this x2 bar to estimate mu. But the problem is these two, they are different. Okay, however, in the population, the mean parameter mu should be just a one value. Okay, so these two, they are different, so we have a problem. If we consider 100 samples, we will be having 100 different estimates. So that's the problem in this setting. So in this question I have mentioned that problem. We will be having many possible values for the particular parameter. That means we will be having uncertainty, because we don't know which one is correct or which one is the closest to the actual value. So statistics, the subject statistic is the language to talk about the uncertainty. So yes, we have some techniques to deal with this uncertainty. We know this one. We know these statistics, okay, the measurements in the sample, they depends on the sample. They depends on the sample. So this, it varies from sample to sample. So uh, we can simply consider many samples instead of a few samples. Okay, using the stat key, you can simply go to the stat key, and in the middle you can see there is something called sampling distribution, and click on the mean in the sampling distribution, and you can simply generate a sampling distribution that I showed you in the class. Okay, so here I'm not going to repeat the same thing again, so I'll skip this slide, but I need to explain what is going on with this sampling distribution. So suppose I'm taking many samples to overcome that issue. Okay, so I'm taking sample 1, sample 2, and dot sample, let's say simple k is a k can be any number, uh, any counting number, 100, 200, right. From these each samples I'm taking their mean. So first one, since it's sample 1, I'll denote the sample mean for that sample is x1 bar. For the sample 2, x2 bar, dot dot dot. For the sample k, kth sample, it is xk bar. Okay, these are general notations. Okay, however, these are in single values. Right, now I can consider, let me change the color. Now I can consider, sorry, now I can consider all these x bar values in each sample. They are different, and then I can plot them using a dot plot. Okay, so this is a dot plot. If I do that, I will get this kind of plot. Here maybe you have x1 bar, here x2 bar, here xk bar, something like that. Okay, how many x bar values here? Same number of dots here on the dot plot. So this we called this distribution. This looks familiar, right? See, bell shape. So this we called sampling distribution. Sampling distribution, because this distribution or the shape based on sample means. Okay, based on samples, so we call sampling distribution. Using this sample distribution, we can measure or we can calculate x bar and simple as standard deviation. Okay, mean and standard deviation. We can talk about this. Okay, mean somewhere here, standard deviation this much. The uncertainty I told you earlier, which is this standard deviation. So we'll talk about the standard deviation a little bit further in upcoming slides. Okay, so this is the definition about the sampling distribution. It's a distribution of sample statistics. See, sample statistics computed from different samples. So it's obvious, because when we take sample and calculate the statistics, they are bound with, or they are directly depend on the sample. Sample sizes are the same. This shows the sample statistics, how they are varies from sample to sample. Okay, how they change sample to sample. Right, in the sampling distribution, since it looks like this, it has a mean, or it has a center, and also we can measure the shape, or we can measure the spreadness by using standard deviation. So when we are taking samples to generate, to generate 1,000 samples, 100 samples, the number of samples, we simply use random sampling technique to make things random. Okay, so that we can get the sample measurements or the statistics closer to the center. Closer to the center mean around here. So they will not go beyond the center. Okay, and also if we can pick a large enough sample. So large enough sample, it depends. So there's no specific numerical value for this large enough. Okay, so large enough means large enough. So if we can pick a large enough sample, then we can keep this bell shape. Okay, that means this skewness we can control. Do you remember the skewness, how it changed, or this spreadness, how it works with the standard deviation? When standard deviation goes up, your plot gonna be more flat. Okay, when standard deviation getting smaller and smaller, your smaller and smaller, your distribution become like this. It narrowed down around the center. Okay, right. So using this sample distribution, we can talk about the variability, what is going on here in. So if you take a random sample, I mean always all the time. I don't want to talk about if you take random samples. This is what we do all the time. So when I tell you to take a sample or consider a sample, normally that means you are considering a random sample. Okay, so if you are considering random samples, then the sampling distribution will be centered around the true population parameter. Centered around true population parameter means it is a center measurement, so it is centered around mu. Okay, true population parameter. And center and the shape we talked about in chapter 2. So the variability we measure by using the standard deviation. Measure by using standard deviation. Here actually in the stat key sometimes use another word for this standard deviation, especially in this chapter. Standard error. Standard, sorry, standard error. You will see this a lot. This standard error is exactly same as the standard deviation. So whenever you see standard error, that means the standard deviation. So there is no difference. Okay. So this measure standard error or standard deviation can measure the uncertainty or the variability, or in other words, we can tell how far it spread out from the center. Okay, so we are trying to address the uncertainty in this statistic, the sample measurements. So so standard error is the measurement we use, standard error or standard deviation. Okay, standard deviation. It's a statistics. Normally, this is standard error we denote by using SE, capital S and E, standard error. Okay, is the standard deviation of the sample statistics. So they are the same. It measures the standard error. It measures how statistics variate from one to another. Okay. So the next thing is the size. To keep the shape of the distribution, or simply in other words, we can tell to reduce the spreadness. Okay, we need the sample size. So this is the this is the relationship. Let's say the sample size is capital simple n. Normally we use simple n. So when simple n increases, okay, standard error, or I'll use standard deviation. Okay, or we'll call variability, same things. Okay, variability goes down or reduces. Okay, on the other hand, the opposite, uh, sample size. This is about sample size. If you pick a one sample, how many elements or how many objects are in that sample, that's the sample size. Sample size goes down, that means the smaller sample, they have very big variability. For large sample sizes, you get less variability in the statistics. That means less uncertainty in your estimates. in your estimates. Right. So these are very important facts, but we will we will solve some problems. We will go through some computational stuff, starting from section 3.2. Here in section 3.1. I just need to give you a brief overview about what is going on with these estimates. So you should know what is an estimate or what is an estimator, what we do with this sample and population, what are the parameters, what are the statistics. So you should be able to understand these two clearly. How we can conclude the population based on the sample, the statistical inference. Okay, so you should be able to talk about these things. So we estimate population. They talk about the uncertainty because the statistics varies from sample to sample. So to overcome this issue, we came up with an idea about sampling distribution. Take the means of all samples and plot them, plot a dot plot. Then we can find the sampling distribution. Standard error, that is exactly same as the standard deviation. Okay, this standard error can measure how uh, how these statistics um, deviate from their original values from sample to sample. Okay, all right, so I think that is the end of the section 3.1, and I think now you have a better idea about what we are dealing with or what we are going to deal with in this chapter. Okay, there are only four sections, and this chapter 3 is super easy. You have to get this idea, you have to remember this idea in order to move forward. All right, I'll see you in the class. Take care.